Hi everyone, Dr. Gray here. Today we are working on Waves Target 4, understanding how waves act and interact. Understanding the behavior of waves is caused by reflection, refraction, and absorption, and understands how reflection and absorption produce color. And as you can see from our title here, we're going to focus on refraction and lenses. So we're looking at how waves act and interact and the behavior of light in terms of refraction. So refraction is the bending of light that occurs when a wave enters a new medium. And so we could be talking about light waves. Light waves are easy to think about. Light waves, if they are traveling through the air and then they pass through a window, well, that window is a new medium. And so when they pass through that window, those light waves bend. If that light wave is traveling through air and then is traveling through water, the water is a new medium and so it bends. If we have, if you look at our picture down here, we have light waves coming in. They pass through glass, that's a new medium. Glass into water, that's a new medium. Then they travel back through glass, so a new medium, and then back into the air. And so the light waves in this picture down here are bent and rebent over and over again as they pass through different medium. So there's some interesting phenomena associated with refraction. We get rainbows as a result of refraction. We get this sort of odd phenomena here where it looks like the straw that's in this glass of water is in two parts, when it's certainly not in two parts, but that is an example of refraction as well. And so if we're talking about light entering a new medium, we're going to draw a ray diagram. And so in this ray diagram, there's some information here that we're going to need. So this line here represents the interface, where we have, in this case, let's say we have air above and we have water below. And that line in the middle is where the air and the water are in contact. And then we have this dashed line that runs down, it's perpendicular to that interface, and this is our normal. We learned about the normal when we were talking about reflection, but that's the normal. It's our imaginary line that's at a 90-degree angle to that surface. And so when it comes to refraction, if we're talking about a light wave, for instance, we have our light wave, which we represent with a ray. An array is a ray is just an arrow. It tells us what direction that wave is traveling. And if this light wave were traveling through air and it suddenly entered water, well, it's going to slow down when it encounters the water and it's going to bend toward the normal. And so it's not going to continue traveling in a straight line. That doesn't happen. Instead, the wave is bent. So the reason that the wave is bent, the reason that the direction it travels changes, is because the speed at which it travels changes. We don't often think about it, but light doesn't travel the same speed in all different kinds of media. If we think about the speed of light in a vacuum, and so this is the speed of light as it travels through space. Light travels through the vacuum of space at about 300 million meters per second. That's really, really fast. Here on Earth, when light travels through air, so air is a gas, there's not much to slow those particles down or slow that light down, but it does slow down just a little bit. The speed of light in air is about 299 million meters per second. In water, now the particles are very close together. The light wave is slowed down considerably by those particles being close together. In water, light travels at about 227 million meters per second. And in diamonds, just so we have a solid here that we consider, light travels through a solid like diamond at 125 million meters per second. And so really, you don't need to know the actual speeds that light travels in the different mediums. What you want to pay attention to is the relative speeds. It is fastest if there is nothing to impede its flow, and it is slowest in solids. And so we decrease in speed as the density of the matter increases when it comes to light. Now, sound waves are mechanical waves. They depend on that medium to transmit the energy. And so they have the opposite trend or the opposite pattern in terms of how the speed of sound waves travel. For instance, sound waves do not travel through a vacuum because there's no matter to transmit that vibrational energy. The speed of sound in the vacuum of space is 0. It doesn't happen. In gas, well, you can hear me talking, so that means that the sound waves are traveling through the air. Sound waves travel through air at about 344 meters per second. And it's important to know that that value changes as the temperature of the air changes because temperature affects the density of that air. But 344 meters per second, that gives us a pretty good idea. In water, well, water is a more dense medium than air, and so sound travels through water at a speed of 1,484 meters per second. And for comparative purposes, not that I put my ear up against a diamond or talk into a diamond very often, but the speed of sound in a diamond is 12,000 meters per second. And so here we see the opposite trend. Here we have fastest for the solid, slowest for the gas, and sound waves do not travel at all through the empty vacuum of space. So in preparation for being able to draw ray diagrams to show how light is refracted, let's use a car analogy. Let's imagine we're driving a little car and we're traveling along on the road, and all of a sudden we encounter a mud puddle. And if we're driving straight, if we encounter that mud puddle head on, then when we hit that mud, right? So here's our roadside. This is the mud. Well, so when our car hits the mud, both front tires are going to slow down simultaneously, and that's going to cause the car to just slow down. But if we're traveling at an angle, we get something different. And so let's look at this car. This car is traveling at an angle. Well, when we're traveling on the road, both tires are moving at the same speed. But when we encounter that mud puddle, the red tire here is going to encounter that mud puddle first. And so it's going to slow down. But the yellow tire isn't going to slow down. It's going to keep going the same speed. It's going to keep moving forward, where the red tire, because it's going to slow down, I'm going to put a little backwards arrow. It's not really going to turn backwards, but it's going to slow down. And if we draw a little backwards arrow, it helps us to kind of visualize how that car is going to turn. The yellow tire is going to keep going forward, and since the yellow tire still moves forward at the same speed while the red tire slows down, it's going to cause the car to turn towards the normal. Now let's look at the other situation. If we were driving through mud and we suddenly get out of our mud puddle, both of those front tires are both going to start speeding up, and so the car is just going to go faster as soon as we get out of that mud puddle. But if the car is driving at an angle, just like we saw in the previous case, we're going to see it's going to bend. Well, now, here we still have the mud on this side. Our road is on this side. Here we're going to see the opposite effect. Instead of the car being slowed down when it encounters that road, it's going to speed up. But the red tire is going to speed up first because it's going to hit the road first. This tire is going to speed up first. This tire isn't going to go backwards. It's just not going to be going as fast. And so we put a little backwards arrow to help us see how that's going to turn. When the car that's traveling through the mud at an angle encounters the road, it's going to bend away from the normal. And this is true whether we're talking about light waves or sound waves. We want to think about, is the wave speeding up when it encounters that new medium, or is the wave slowing down when it encounters that new medium? If the wave slows down in the new medium, it will bend toward the normal. If the wave speeds up in the new medium, then it's going to bend away from the normal. So I mentioned earlier that rainbows are phenomena that are the result of the refraction of light waves, and that refraction occurs as the light waves are traveling through the atmosphere and they encounter a new medium, and in this case the new medium is water droplets that are in the atmosphere. Did you know that there can also be moonbows? So they're formed the same way. We have light waves that are moving through water droplets, only now the light waves are the reflected light waves that result from moonlight. As you might imagine, they're pretty rare, but I have included a picture here for your enjoyment. So let's look at how that happens. For starters, let's just look at how a rainbow is produced when white light passes through a prism. And so this gray triangle here represents a prism. And so the white light enters the prism, and white light is just a combination of the different colors of visible light. And so right here, it only shows the red, orange, green, blue, and violet. So the red, yellow, green, blue, and violet. The orange isn't in here, and you can't really see the indigo, but you can imagine. So here we have our incident light rays. Notice that they are all parallel, which is why they combine to produce white light. In terms of refraction, we have to consider each of these different colors of visible light separately because they're going to behave differently in each case. And so now here on the side, we have these little lines. Those represent the normal. And so outside of the prism, the white light, or our light wave, is traveling through air. When it enters the prism, it's either going to be traveling through glass or plastic. Both cases, that's a solid, and so the light wave is going to slow down. And what I want you to notice is that in every case, each different color of light bends toward the normal when it enters that prism. It slows down, and so it bends towards the normal. Now, you've probably noticed that each wave was bent just a little bit differently, and that's because the amount of bending is going to depend a little bit on the wavelength of each light. And since red light has a longer wavelength than purple light, it is bent least. The smaller the wavelength, the more it is bent. But we're not finished. That light wave is going to continue traveling. When it gets to the other side of the prism, now it's going to enter a new medium. It's going to travel back into air, and when it moves into the air, it's going to speed up. And so now it's going to bend again, only this time it's going to bend away from the normal. And so here are our normals. Remember, they are perpendicular to the surface, and here we see that our waves are bending away from the normal. Rather than traveling in a straight line, they bend away from the normal. And just like we saw before, the greater the wavelength, the less it's bent, the smaller the wavelength, the more it's bent. And so when the waves come out, or when the light waves exit the prism, moving into that new medium essentially has the effect of spreading out those light waves for us to see even more. So rainbows are produced by prisms because the light waves are bent upon entering, bent upon exiting, and that bending spreads out the different colors that make up the white light and makes it visible for us to see. Now, it doesn't have to be a prism. We also form rainbows with water droplets. And so, in this case, the water droplet is going to serve the same purpose as the prism. It's going to cause the light to bend. It's the new medium. Now, water droplets are, of course, liquid, not solid, and so the light wave isn't going to be slowed down quite as much moving into the liquid, but it has to enter the water droplet and it has to exit the water droplet. And just like with the case of the prism, when the light wave enters that water droplet, it's going to bend toward the normal when it slows down. Now, something extra happens in a water droplet because the light wave actually does what we refer to as internal reflection. And so some of the light wave is transmitted out. And will bend upon leaving that water droplet. But most of the light is reflected inside of that water droplet. And when it exits, if we put in our normals here, we see that Upon exiting that water droplet, the light wave moves back into the air, is going to speed up, and in this case, bends away from the normal. And that is how that's what produces light. That's what produces rainbows. Now, you'll notice that in every picture of the rainbow that I showed you earlier, rainbows always have the red on top and the purple on bottom. And that's because of where you are when you are viewing the refracted light coming through those raindrops. And so, of course, in the sky, when we can see a rainbow, there's not one water droplet, there are billions of water droplets. And each water droplet is separately refracting the light. And so here you are as the observer, and because of your position, what you see are the light waves that encounter your eyes or that are refracted into your eyes. Water droplets that are at a higher altitude, well, they're going to create their own little rainbows, but you're only going to be able to see the red light. The blue, the purple, the green, those are all going to go over your head. The water droplets that are at a lower altitude, well, they also create little raindrops, but you're going to only see the purple or the blue. The red, the orange, the yellow, those are all going to be directed below you. And so that's why the red in our rainbow shows up on top, and the purple in our rainbow shows up on bottom. So the next phenomena that's associated with refraction that we want to look at is vision. And so let's talk about how vision happens. We all know that in your eye there is a lens, but most of the refraction that happens in vision isn't done by the lens, it's actually done by the cornea, which is this section of the eye. And so that's what bends the majority of the light. The lens actually it fine-tunes what you see. It fine-tunes how the light is bent in order to enter the eye. In healthy eyes, if you're going to look at something at a distance, the ciliary muscles contract to tighten up that lens, make it a little narrower to help focus that light that comes in. If you're looking at something up close, well, now the ciliary muscles relax, the lens gets a little larger, and the waves are bent, or the light waves are bent a little differently so that you can focus on that object that is up close. So before we get into how do glasses or contacts correct poor eyesight, let's look a little bit about how lenses work in the first place. We're going to start with the convex lens here. And the reason we're going to start with the convex lens is because the convex lens is most like the lens that is in your eye. A convex lens is a converging lens. And converging means to bring together. And so in a convex lens, what happens is here's our incident light rays. Incident light rays are parallel. And what that converging lens does is it bends those light waves together. And so that's what it means to converge. And this is how the lens in your eye functions. It draws together those incident light waves and focuses them at the focal point. And we'll talk more about that in a moment. Now, the other type of lens we have is a concave lens. Technically, this is a double convex lens because both sides have that convex curve, and this is a double convex lens. And a double convex lens is a diverging lens. And so a double convex lens doesn't bring light waves together. Instead, it spreads them apart. That's what it means to diverge. And so the light waves pass through this double concave lens and they spread apart. So if you're a corrective lens wearer, if you wear glasses or contacts, you're probably thinking, oh, well, I'm nearsighted or I'm farsighted. And you can check it out. You can take out your glasses and look at it. If you are nearsighted, then you're going to wear this kind of lens. You're going to wear a diverging lens. If you are farsighted, well, you're going to wear a converging lens. You're going to wear a convex lens. And we'll talk more about that in a little bit. But first, let's look at the ray diagrams for lenses. So let's start with this double concave lens and draw a ray diagram for this double concave lens. And so we're going to look at this tree. Don't make fun of my drawing. We're going to look at this tree through a double concave lens. And we're going to follow the rules for how to do this. Our first rule is we're going to draw a ray from the top of the object, that's my tree, parallel to the optical axis. And the optical axis is this black line that runs through the center of our lens. Now, as this light wave travels and encounters this lens, it's going to change medium twice. It's going to change medium as it enters the lens, so it's going to bend when it enters the lens, and it's going to bend again when it exits the lens. And so to think about how it's going to bend, let's put in those normals. Remember, the normal is perpendicular to our surface. And so first, let's just put in, we're going to draw a ray from the top of the object parallel to the optical axis. And there it is. It's just about to hit our lens. And let's think about, where is our normal? Our normal is perpendicular to that surface, so it's about there. It's going to slow down when it enters the lens, and so it's going to bend towards the normal. And so it's going to be kind of hard to see this here, but it's going to bend upwards. It's going to bend towards the normal. Then it's going to exit. When it exits, it's going to bend again, and it's going to speed up. And so that's going to cause it to bend away from the normal. Well, both of those effects are going to combine, causing that light wave to bend away from the normal. Now, if we look at the rules here, it says this ray reflects through the focal point. Well, it doesn't really reflect. It does, in fact, refract. But if we think about this light wave out here, this light wave isn't parallel to anything. It's not going to intersect with anything. And so that's not the part of the light wave that we're interested in. We're interested in the part of the light wave back here. And so that's why we say it reflects through the focal point. And so it actually refracts, but we're gonna draw it backwards so that it lines up with the focal point at this position. The next thing that we're going to do is we're going to draw a second ray. We're going to draw a ray from the top of the object through the lens at the optical axis. And so we want to draw the lens, or draw our ray from the top of our tree here through the lens at the optical axis. So let's draw that. And this ray is not refracted. And so this ray, let's see if I can do this now, through the optical axis, sort of like that. And where these two rays intersect, which is at this point right here, that's where the image is formed. And so we get a little bitty tiny tree right there. Again, don't make fun of my drawing because I'm not very good at it. So double concave lenses do never produce real images because this light wave and this light wave don't actually intersect. They're actually, and the image is formed here by sort of a virtual realm. This is a virtual image. What that means is that image could never be projected onto a screen. So let's look now at the ray diagrams for double convex lenses. Now, instead of doing a tree this time, I'm just going to do a little arrow. Maybe that'll be easier to draw. No, not really, but that's okay. You get the picture. All right, so here are our rules. First, we're going to draw a ray from the top of the object parallel to the optical axis. This ray refracts through the focal point. And really, it's the same rule that we saw for concave lenses. And so it's parallel to the optical axis, and then it's going to refract through the focal point, and that's this F. And so it's going to get bent this way. Our second rule, we draw a ray from the top of the object through the lens at the optical axis, And just like with the previous one, this ray is not refracted. And so through the lens at the optical axis, and so we want it to intersect right about there. There we go. And just as it was before, where these two rays intersect is where the image is formed. Now notice that they intersect below our optical axis now. And so that causes our image to be inverted or upside down. And so here is where our little arrow would be. I did a better job that time. And so we get, it's a real image because it's produced by actual light rays passing through it, but it is inverted. It is upside down. Now notice that a double convex lens like what we see here is the same shape as the lens that's in your eye. And your lens, remember, the lens in your eye has to look at things at a distance and it has to look at things up close. And how it works at a distance and at up close is actually slightly different. And so our first one we did here, we have our object is greater or is further away than the focal point. It is actually at about 3 focal lengths from the lens. Let's look at what happens if the object is close up. And so this first object, this is something that's far away. Now let's look at something that's close up. And so for this one, I will draw this one in red, or I will try. We're going to put it right about here. So I'm just going to do a rectangle. Maybe I shouldn't do a rectangle. Maybe I should do, let me try and do my best effort at a arrow. It's very hard to draw with a stylus. And so now we're going to follow our rules. We're going to draw a ray from the top of the object parallel to the optical axis, and it's going to refract through the focal point. And so it's going to start out similar. It's actually going to be very similar to this other one because it was the same height. And so it's going to go this way and refract through the focal point. The second one, our second rule says draw a ray from the top of the object through the lens at the optical axis. This ray is not refracted. So here we're going to see something different now. When we start at the top of top of the object and draw it through the optical axis, what we see is that in this direction, these two blue rays are never going to intersect. Not in that direction. And so in order to find out where they do intersect, we have to actually extend them backwards. And so we're going to extend this one back this way and this one back this way. And they actually intersect back here. And so now our image is, this is a virtual image, because it is not created by the light rays actually passing through it. And so unlike our black arrow, this one could not be this blue arrow could not be projected onto a screen. It is a virtual image. It is, however, in the normal orientation. It is formed above the optical axis. And so this one would be virtual, but it would have a normal orientation rather than the inverted. And so convex lenses, you can have real images or real images or virtual images. It depends on how close the actual object is to the lens itself. I invite you to ask me in class to look or to play with a double convex lens so that you can actually see how those lenses behave. All right, so let's go back now to talking about how the eyes work and how corrective lenses work. First, let's talk about the different types of vision. We have normal vision, and so if you don't wear glasses and have no need for glasses and you can see everything clearly, the reason why is because those incoming light waves are accurately refracted by the cornea and the lens of your eye so that they focus on the back of your eye. Where their focal point is in contact with that retinal nerve and where the cones and the rods are that pick up that eye or pick up that image. If you are farsighted, you are hyperopic. The farsightedness is hyperopia. And if you are hyperopic, that means that you can see things that are far away, but you can't see things that are up close. And the reason that you can't see things that are up close is because when that object is close by, the incoming light waves are not refracted quite enough. The focal point for someone who is hyperopic is actually behind the eye. And so instead of seeing a clear image, a hyperopic individual, a far-sighted individual that's trying to see something up close, sees a blurry image. Now, the other case for those that require corrective lenses they are nearsighted. And nearsighted means you can see things that are up close, but if it is at a distance, then those images are blurry. And this is known as myopia. I myself am quite myopic. I can see clearly about 6 inches away from my face if I don't have my glasses or my contacts in, but past that, everything is blurry. It has been that way since I was in about the 4th grade. So in the case of myopia, what happens in this case is now the light waves are refracted too much. They are refracted too much, and so instead of them coming to a focus on the back of the eye, they come to a focus just in front of the back of the eye. And so the retinal nerve and the cones and the rods in this case are not getting enough information, and so again you get a blurred image. Well, in order to correct whether it's hyperopia or myopia, we have to adjust how the light rays are refracted so that they focus on that retinal nerve in the way that they're supposed to. For far-sighted individuals, a double convex lens is used, and the function of that convex lens is, notice that those light rays begin to refract before they enter the eye. And so that when we add the refraction from the eye to the refraction that's caused by that corrective lens, now the light waves come to a focal point on the back of the eye, and that allows the brain to interpret that image clearly. In the case of nearsighted individuals, well, because the light without corrective lenses focuses in front of the retinal nerve, we need to slow that process down. And so a double convex lens is used, and you'll notice that right here that the lens causes the light wave to diverge. It causes it to spread out a little bit, so that then when it gets into the eye causes it to converge, and now, because the light waves were spread out a little bit before they got to the eye, the convergence that happens by the lens in the eye causes the light wave to be focused on that retinal nerve and gives us a clear image. So your follow-up assignment for today's lesson is I want you to write me a paragraph summarizing what you have learned about refraction. Your paragraph, and it just needs to be one paragraph, a well-written paragraph, needs to include information about what is refraction, what happens to light during refraction, or what happens to a wave during refraction. How does the density of the medium affect the movement of a light wave? In other words, what happens when light goes from being in the air to in water to in a solid? Does it speed up or slow down? We want to know what's going on. Does the medium cause that wave or allow that wave to speed up or slow down? And what's the general rule for regarding how light bends? Does it, when it moves into a new medium, into a denser medium, does it slow down? Does it move when it moves into a denser or a less dense medium? Does it speed up? What's the general rule so that we could do that with any kinds of waves? Remember, refraction is a wave property. It is not a light property. It is a property common to all waves. And so we can talk about refraction not only of light waves, but we can talk about refraction of sound waves, of seismic waves. Waves refract. And so we need to have a general rule for how refraction occurs. And then give some examples of refraction of light waves. I think today's lesson you'll have seen several of those. In addition, if you are so inclined, please let me know, what did you find most interesting about refracted waves? What would you like to know more about? And where would you like to go from here? If there's more that you would like to learn that might follow up refraction, let me know. And if you're still confused or lost on something, please include that information in your paragraph as well. That's it for today. I'll see you in class.